that we do as the full posterior distribution. An estimate is a number that you might choose to get from that distribution. You might choose the mean or the mode and just reduce things to a single number, but you don't have to do that, and in some ways there's not necessarily any point. So the output really is the full posterior. So I want to talk about a different class of problem now, which is to talk about model selection. So what we've done so far is basically assumed a single model. So we have a framework, which might be lambda CDM or some other model, and we want to infer the parameters of that model. So we're concerned with a single model. But there are other questions that we might be interested in, which are higher level problems, higher level questions, such as, well, is lambda CDM the right model? Or do we live in a braneworld cosmology or a steady state theory? You know, those would be all different theoretical models. Do we have Einstein gravity or do we have F-bar gravity? Completely different models. They may have different sets of parameters. I mean, we may well want to ask the question, do the data favor one particular model over another? Where we're not concerned with the parameters of the model, we're concerned with what's the probability of the model. So, different models can mean different things. So it may be that we're talking about different physical models, but in many circumstances, a different model can just be a question of adding in an extra parameter into the model. So I could, for example, regard flat lambda CDM as a model, and lambda CDM as another model. So they're very similar. Those would be examples of a nested model, where the flat model is one special example of the more general model. It just has only the curvature equal to 0. So it's part of the wider model, but you don't allow the omega curvature to vary from 0. So one way to look at those is, those are two separate models. One of them has, let's say, 6 parameters, and the other one has 7. And they have 6 in common. Now in the latter case, when you introduce a new parameter into a model, then if you look at the likelihood, then the likelihood is going to be at least as good as the simpler model, simply because since the simpler model is already in the bigger model space, then you know that the maximum likelihood of setting the curvature to 0 is going to be, you're going to do at least as well as that if you allow the curvature to vary. So using the likelihood itself is dangerous, because you will almost certainly always favour putting in an additional model. So how do we do this in a Bayesian way? Well, here's just an example which I go at. Let's take some data from the expansion of the universe. We could have two models. One is that the universe is not expanding, that B is equal to 0, and that's the model of Mrs. A. You seem to have changed sex between the first and second line, so sorry about that. But Mr. B has a theory. Mr. B has a theory that there's a linear relation with this between them, and that has a single parameter in it. So the first model has no free parameters. The second one has one parameter in it. So let's have a look at the Bayesian approach to model selection. Let's consider two models, M and M dashed, and we just do the same sort of procedure for this as we've done before, which is to apply rule 1, which is to write down what is it that you want to know. So clearly, if we've collected a set of data, X, what we want is the probability of a model given the data that we've collected, plus any prior information that we might have had. So that's the quantity that we need to calculate. How do we do it? Well, we'll use Bayes' theorem. We want P of n given x. So these problems are generally very similar to each other. You use Bayes' theorem to reverse the order, because the probability of getting the data given the model is something that we can hope to be able to calculate. So use Bayes' theorem, and then the relative posterior probabilities of two models just comes from taking the ratio P of m of x, or m prime of x divided by P of n given x. So here the thing on the bottom, the P of x here then cancels out, and we just have the ratio of the prior probabilities for the two models, so the prior probabilities of the models. So that's something which you may choose to set to be equal. You may say, without any data, I just regard the models as being equally probable. That's the normal situation, unless you have a particular reason to favour one over the other. You can set this to ratio to the unity. And then we have the probability of the data given the model. And we can write that by marginalising, or inverting the marginalisation, as an integral over the parameters of the model times the likelihood function, the probability of the data given the parameters in that model, times the prior distribution P of eta prime for that model. So this looks just the same as we've done before. The only thing that I've done is to very explicitly record the dependence on the model in all of these probabilities. So you'll notice that the integrations here over the parameters may differ between the two models. They may have a different set of parameters. Typically they would. They wouldn't necessarily have the same parameters. So we define a thing called the Bayes factor, which is just the ratio of the evidences. So these integrals are called the evidence, and that's the evidence ratio is called the Bayes factor. So if we assume that the model probabilities are equal to each other, then if we do an experiment, then we update the probabilities by the Bayes factor, by the ratio of the evidences. Okay, so this is the relative probability of models given the data, assuming that the model priors are the same. So what do we do with this? Well, let's just think a little bit about computing it. So the evidence, sometimes we see it called the marginal likelihood, is the probability of the data given the model, and this is an integral over the parameter space. So this is a multi-dimensional integral in typical cases. It's the integral of the likelihood times the prior. And it's the denominator that we had in parameter inference. It's the thing that appeared on the bottom in parameter inference that we ignored for parameter inference because it cancelled out when you took the ratio of probabilities. So just to go back to what we did before, if we were looking at if we're doing parameter inference, the probability of the parameters given the data was the likelihood times the prior divided by this evidence. So this evidence is the thing on the top. So if we just are a little bit more explicit here, then when we do this, we always have a model in mind. So I should perhaps make everything conditional on the model. And then you see that the term on the bottom, P of x given n, is the evidence. So that's what we need to calculate if we're going to get the model probabilities. Let's say that we've managed to do that. We've calculated model probabilities for more than one model. One more comment on this, that this is generally a very expensive thing to compute because you need to do a multi-dimensional integral over the parameter space. So I'll come and make some remarks about how one does this in practice. But evidence calculations are now being done, but they're a relatively recent addition into doing into cosmological data analysis, simply because of the computational challenges of doing these multi-dimensional integrals. Okay, so let's say that we've calculated the evidence for two or more models. You can then assign a posterior probability for the models. If you have n of them, then you just take the evidence divided by the sum of the evidences of all of the models that you've looked at. And that will be the posterior probability of the models, provided that the set of models that you've considered is exhaustive. That, in other words, one of the models that you've considered is the right one. So this sort of evidence calculation includes some elements of Occam's razor. So if you have a model which has many more free parameters in it, then you'll get better likelihoods. But there must be some sort of penalty to pay, because otherwise we would always favour the more complicated models. And Occam's razor says that if you don't need to introduce extra parameters into the model, then you shouldn't. There's a sort of hope that the models are simpler. So Einstein's view of this was to say, make everything as simple as possible, but not simpler. So if you make it too simple, the likelihood will be very bad because it won't be able to fit the data. So don't make it too simple, but don't make it too complicated either. And the Bayesian formalism includes some elements of that in the way it works. Just to say, what do you do when you've got these Bayes factors? Well, there's a traditional scale for interpreting the Bayes factors, called the Jeffreys criteria. I would suggest you do not use Jeffreys criteria because I think they're far too loose. His suggestion was that if the logarithm of the Bayes factor was between 1 and 2.5, you regard that as substantial evidence. But I don't think that's very substantial evidence. Log the Bayes factor of 1 corresponds to a posterior probability for the less favoured model, which is 0.37. So that's not very disfavoured. So I would not regard that as substantial evidence in favour of one model over the other. So I would demand much larger values of the Bayes factor than the Jeffreys scale suggests. Let me give you an example of an evidence calculation where the Bayesian view would give really quite a different answer from the frequentist view. As you're probably aware, most particle physicists are committed frequentists, and this is some data from Atlas from the LHC, comparing two models for the Higgs boson, one which is a model where the spin and parity is 0 plus and the other is 0 minus. So these are the likelihoods. So here, there are probably more parameters in the model, I don't know, but if there are no parameters in the model, then the evidence just ends up being the likelihood. So these are the likelihoods for the two models, and the data is the solid vertical line here. So the frequentist analysis that the particle physicists would do would be to say, well, this value is perfectly consistent with the blue curve. So the 0 plus model is fine, but it's right out of the tail of the probabilities of the 0 minus model. And they work out that it's ruled out at 97.8% confidence level. The tail here at 2.2%. So the Bayesian view would be to say, let's work out the ratio of the evidences so we can work out the probability of the two models, 0 plus and 0 minus. And there, the ratio of the probabilities of the two models is just the ratio of the value of the likelihood of the blue curve here to the likelihood of the red curve at the measured point. And if you work out this ratio, then it's around about, reading the numbers off the graph, it's a ratio of about 11. So the 0 plus model is favoured reasonably strongly, by a factor of 10 or so, but not overwhelmingly. It's certainly not something that particle physicists would regard as at all significant. Well, they wouldn't regard 97.8% as significant either. But the Bayesian view would be to say that these models, the difference between the probabilities of these two models is a good deal less than the frequentist analysis would tell you. We would be much less sure than the particle physicists. Yeah. Sorry, who's right? Well, I would say the Bayesian result is right, because that's the principal statistical way of doing it. So the frequentist result tells you something about the probability of getting the data given the model. So that says the probability of getting the data out in the tail, or further out in the tail, is 2.2%. So that's a very precise statement that says that if the model is 0 minus, and the probability of making a measurement that's here or further to the right is 2.2%. Very precise, I have no qualms about that, I'm sure that probability is perfectly correct. But it's the probability of something that I'm not interested in. I'm interested in a different question, which is, given this value, what is the probability that the red model is the right model? That's a different question, it's the other way around. So the Bayesian framework gives you an answer to the question that I think is the interesting one.
What about if you have a model that has more parameters?
I'll come to that in a moment. Yeah, that's yeah. We'll cover a model like that. So ask me questions if that's if it's not clear after that. Just to say that evidence calculations tend to be a little bit conservative because they have this Occam's razor element built in. So generally speaking, you need to in a sense disfavor the simpler model by quite a bit before the Bayesian evidence will say no, the simple model is not adequate. So here's an example from some calculations we did before to contrast Einstein gravity with other gravity models that have different growth rates. So this is what we would expect from the Euclid experiment for the log of the base factor, assuming that the growth rate, which differs in these different models, different gravity models, if it differs from, in reality, if it differs from Einstein gravity by the amount that's given along the bottom, what would the experiment tell us? We have to do the experiment to do it. This is an analog, if you like, of doing a Fisher matrix calculation, but for evidences. What would we expect to see? And here, this is the modulus of the log of the base factor. And what it means is that if the difference between the true gravity model and the Einstein model gives you a difference in the growth rate, which is less than about 0.03, then the Euclid data, recleansing data, would favour general relativity. In other words, the gravity model had better give you a growth rate which is more different from general relativity by at least 0.03 before it will start to favour the other model. DGP, for example, is way out here, so Euclid, I mean DGP is not a particularly favoured model, but Euclid would give an evidence ratio which was very large because it's so far away from the GR result. So that would be a relative probability of e to the power of 30 or something. So it's a very, very significant preference for DGP if that's the right model. But if the model is not far away from GR, then even if the model is really not GR, then the evidence would say, you know, Occam's razor is in operation. GR is good enough. It's not it's favored by the data. So how do we do the calculations? Well, it's challenging. It's thought that if you use chains from MCNC that you can't do it, and I'm not actually certain that that's correct, but it's not thought to be a good way to do it. The way which has been favoured recently is a thing called nested sampling. I'm not going to go into the details of this, but just to sketch out how it works. That if you draw some points at random from the prior, and then you find the lowest likelihood point, and you throw the lowest likelihood point away, and then you generate a new point which has a likelihood which is higher than this one, appear somewhere in here, and then you repeat the process, you remove the lowest likelihood point, generate a new one that has a higher likelihood, and repeat that process, you end up with more and more points near to the peak of the distribution, and this allows you to estimate the integral under the likelihood multiplied by the prior. There's some software called Multinest that will do this for you. It's flexible enough to allow for multimodal likelihoods, so it will do the integral over one part of the parameter space, and if it finds some significant probability somewhere else, it will sort of spin off and do another nested sampling calculation there. There's a new version called Polychord that involves some slice sampling methods as well. So that comes from the same people who wrote multi-nest. So I haven't tried it, but it's presumably in advance. Okay, so these are generally quite difficult calculations to do computationally. There are some simplifications for certain types of models. So if you have nested models, where one model is a special case of another one, then you can calculate the evidence with a thing called the Savage-Dickey density ratio. So this is very useful, and Lita is going to lead you in doing some calculations with computations with this later. So let's consider two models, M0 and M1, which have parameters of psi and phi. So here's an example where we have some extra parameters. One model, M1, has some extra parameters. Let's just say one extra parameter just to keep things simple. Then we can work out the Bayes factor. So the Bayes factor probability of M0 given x divided by the probability of M1 given x, which for uniform priors is the same as this ratio of evidences. So we just write down the evidences. The only difference here is that we have extra integrations to do for the more complicated model. So one extra integration for psi. Now if we assume that all of the probabilities are continuous as a function of the parameters, then the limit of the prior for the extra parameter will end up being the same as the prior in the simpler model. So basically we're just saying that we just assume that these are continuous prior. Then we can calculate these Bayes factors. So for P0, this is the same probability in the more complicated model, but with the parameters set to the special value of the count. So these two probabilities at the top can then be expressed in terms of the probabilities in the wider model. We've just set the parameter to its particular value, final. Okay, so the thing on the top, if you look at this, then this is the probability of x given psi, and phi equals final times the probability of psi with phi equals phi naught. And in the extended model, so this is the probability of the data given that phi is equal to phi naught in the extended model, and the thing on the bottom is just the probability of getting the data in the extended model. So that's the same formula written down again. So let's apply Bayes' theorem to this. So the probability of x given that phi is equal to phi naught, we can write in terms of, so this is doing things the other way. We start with the likelihood and we're going to write it in terms of the posterior. So this is using Bayes' theorem in the opposite direction. We can write this like this, it's Bayes' theorem again. So it allows you to simplify the expression for the Bayes factor between for the simpler model over the more complicated model as the posterior in the extended model with the extra parameter. It's the posterior for getting phi equals phi naught given the data divided by the prior for getting that value in the extended model. So it's quite a simple expression. This is the Savage-Dickey density ratio. If you think about it, that actually the posterior, how would you get it? Well, you can use Bayes' theorem the other way and write it in terms of likelihoods, and it doesn't really help. So you need to be able to estimate the probability. But if you've got a sample, if you've done an MCMC, for example, then you can estimate what this posterior is because you've sampled from the posterior. So given a chain, take one of your MCMC chains, if you run chains with a non-flat model, say for supernovae, you can find the points which are close to flatness. So if you take all the points that are within some small distance in parameter space of the simpler model. So let's say you take all the points that have omega curvature between minus 0.01 and plus 0.01, say, and take up the number of the fraction of points that lie in that slice that corresponds to approximately the simpler model, then this posterior will be roughly a fraction of the points that end up near to the flat model divided by the range that you've considered. And that will give you an approximation to the posterior from an MCMC chain. Okay. So you'll do something like this later if you've got some MCMC chains. Let's just look at a simple example of the SDDR. So let's go back to the problem of Mrs. A and Mr. B. Let's say that you do a likelihood analysis for H, and this is what you get. So a peak of the likelihood of about 0.1 in these units with a Gaussian form. And let's take the prior range on H to be minus 1 to 1. So what do you think? Do you think that if you've got data like this, you would think that the model has H of 0, so it's a non-expanding universe? Or do you think these data would favor a model which is expanding with some value of H? What's your intuition? Do you think this is... Who thinks that a model would be favored that has no expansion with a data like this? Nobody? So does everybody think that this would be evidence in favor of an expanding universe if you had a likelihood like this? Yeah? So actually not. So with this prior range, what we have to do is to compare the posterior with the prior at the special value that corresponds to the simple model. So the simple model here has H of 0. So we want to look at the posterior at H of 0 and compare it with the prior. So the posterior here is here, which is at about 1. And the prior here is at a half. So we have to normalize the prior. So if the range of H, prior range is minus 1 to 1 and uniform, then the value of the prior is a half everywhere. So the Bayes factor is going to be the value of the posterior at 0, which is here, which is 1.1, divided by the value of the prior, which is 0.5, so this is 2.2. So these data with this prior would actually favour the non-expanding universe by 2 to 1, so not strongly. Okay. So that's an example where that sort of illustrates that, in a sense, evidence calculations tend to be a little bit conservative. You have to push this likelihood far enough out so that the value of the likelihood at the value of the parameter of the simpler model goes below the prior. So we need to push it a bit to the right in order for it to be favoured. So generally speaking, you need several sigma, if you like, before Bayesian evidence will favour the more complicated model. Is there anything you notice about this that you're uneasy about, or anything that's... how could I change the conclusions given the same likelihood? Right, so the height of this, because it's normalized, the height of the prior depends on the prior range that we choose. So unlike when you're doing parameter inference, where if you collect enough data, the prior doesn't matter. Asymptotically, the prior becomes unimportant. Unlike parameter inference, here the prior always matters. So this is a part of the analysis which is a bit unsatisfactory, have to accept. That if I put a prior range here, which was from minus 0.2 to 0.2, then I would have favoured the expanding model. Okay. But in a way you can see why this makes sense, because we've essentially ended up with a maximum likelihood point which is quite close to the origin. So the sort of question, loosely speaking, the question is, well, what was the chance of landing up close to the origin just based on the prior? And we're comparing that with the actual fact that we ended up close to the origin. So if you make it a very small prior range, then the prior chances of ending up close to the origin are quite big. If you make it a very broad range, then the chances, just by chance, of ending up with something which was so close to the origin would be very small. So it sort of makes sense, but in practical terms, it's a consideration that never goes away. In one dimension, it probably doesn't matter too much, but what I would say is that if you end up doing this in many dimensions, if you have a whole load of nuisance parameters, for example, that you introduce, and you have prior ranges for those, then by changing the prior ranges in multiple dimensions, you can change very markedly the volume of prior space, which can change the evidences a lot. So I would be very nervous about doing evidence calculations where we had many dimensions with prior ranges that we didn't really know very well. So it becomes quite difficult in those cases, and I would be nervous about it. Let me give you an analytic example, which I think is quite instructive. This is one that my colleague Roberto Troppett came up with. Let's consider two models. The simpler model, these are two nested models. The simpler model says that we have one item of data, x, which is drawn from a normal distribution with zero mean and a variance little sigma squared. That's model number one. The more complicated model has an extra parameter in it, and it says that x is drawn from a normal distribution with the same variance, but with the mean which is shifted by an amount of mu. So the extra parameter mu. Sigma squared is fixed, so we just have no parameters in the first case, one parameter in the second case. If we have a prior on mu for the more complicated model that says that it is itself a normal distribution of zero mean and a certain variance, which is capital sigma squared. And let's say we make a measurement, and the measurement is lambda standard deviations away from zero. So the question is, given lambda and given little sigma and big sigma, does it favor a model 1 or does it favor the simpler model 0? Well, we can use the Savage-Dickey density ratio to do that. We calculate the posterior probabilities. These are things that are analytic, so the probability of, give me the details, I think I've got some notes on this which I'll put on the website, where you can do the calculations, you can do these integrals, they're all Gaussians, and you can work out that the base factor in favor of model 0 over model 1 is given by this expression. So it depends on the data, lambda here, and it depends also on the ratio of the width of the likelihood to the width of the prior or the mean. So if you plot this base factor as a function of these two parameters, so the significance of the measurement, if you like, so this is the number of standard deviations away, against the width of the prior divided by the width of the likelihood. And if you're down in this part of the diagram, this would favour the simple model, so there's no evidence that the mean is non-zero. If you're up here in the red parts, then that would favour the data was drawn from a Gaussian distribution which was offset from zero. So this is quite interesting because it shows you a number of things. Firstly, that the pale yellow part here basically says that the data we can't decide between the two models. They're all both more or less equally likely. So in order to get a significant preference for the more complicated model, let's say to get a base factor which is at least 12 times as probable for the more complicated model. That's the middle line of these things here. Then we need to have at least almost 3 sigma deviation from zero. Okay, so anything which is around about 2 sigma away is not going to favour a more complicated model. You certainly need at least about 3 sigma, or maybe even a bit more, depending on how big you want the base factor. And the other thing that you see is that if you're to the left of this plot, then basically nothing has been learned. So in this region here, the likelihood is much bigger than the prior. So if your prior range for the mean is relatively narrow, and your measurement basically doesn't tell you where you are anywhere in that red range, then the Bayesian evidence doesn't favour one model over the other. Okay. But just as a rule of thumb, I think the thing to take away is that you really have to be quite well out in the tails, whatever the value of this thing is, before it will favour the more complicated model. Okay, so one specific example of model testing is, or model comparison is hypothesis testing. This is something which is quite fine in a Bayesian context. If you have 2 hypotheses, you can compare them just by using model selection using the Bayesian evidence. What is more problematic in a Bayesian analysis, and indeed in frequentist analysis, is the idea of rejecting a single model on the basis of the data. In a sense, when you do a Bayesian analysis, you implicitly assume that your model is correct. Or if you look at more than one model, you assume that one of the models is correct. So if you only have one model, you can't reject it or accept it because you've only got one model, so implicitly you say that that is the correct model because it's the only one that I'm thinking about. So unless the likelihood is actually 0, then it will always say that that's the correct model. So Bayesian methods can only do comparisons and give you the relative probabilities of models. So if you're trying to reject a hypothesis, then you're only concerned with one model, so it's not, this is not, it doesn't obviously fit into this framework. So what people generally do is to do frequentist calculations and calculate p-values, and calculate the probability that the data are more extreme than the observed data. So what's the probability that the Higgs thing is further out in the tail than the observed value? And very often, the flawed logic of the frequentist argument is to say if the probability is less than 0.05, then you reject the null hypothesis at the 95% level. It's the wrong thing to do because that's, as I mentioned earlier, is the probability of getting the data given the model. What you really want is to assign some sort of probability of the model given the data, and they're not the same things. The p-value doesn't tell you anything directly about the probability of the model. Other problems with this sort of approach are what does more extreme mean. In simple cases like one of the LHC, it's maybe fairly obvious, but it's not always so. So I want to show you why p-values are misleading and they should be treated with a great deal of caution. So the p-value, as I say, the probability of getting data which is more extreme than the observed one, doesn't say anything about this. Let's analyse this to see what we can learn about p-values. So if the null hypothesis is right, then the p-value has a uniform distribution. If you did the experiment many times and calculated the p-value of the experiment, then you would get a uniform distribution for p. So p is a statistic, it's something that comes from the data. If you just measure p each time for multiple trials in a frequentist way, work out the distribution, it will be uniform between 0 and 1. So it's very simple. So what can we do? Well, one nice analysis that was done by Seliger et al., Sulker et al., was to consider reasonable alternatives to the model, to the null hypothesis. So if we want to consider a class of models which gives you more probability in the tail, and see which is favored. So what they did was to consider a distribution which was for P, which was not flat, not the uniform one, which is what the null hypothesis gives you, but a class of models which gives you more probability for low values of P. This is the range that we're generally interested in, where P is 0.05 or less. So there's a class of probability distributions called beta distributions that have this form here. So as a function of P, they have this form, and psi is a parameter that characterizes the distribution. Psi lies between 0 and 1. The value of 1 corresponds to the uniform distribution. So that's the null hypothesis. Other values of psi correspond to a different class, general class of models that puts more probability into the small values. So we can ask, what is the Bayesian evidence for the null hypothesis compared with this other class of models? So if we do that, we can write down the Savage-Dickey density ratio, which becomes f of p given the parameter 1 divided by the evidence term, so this is the likelihood of the prior. That's f psi, so that should be f of p given psi. There's a symbol missing here. So f of p 1 is just 1 because that's just the uniform distribution. Here we have the beta distribution here and the prior on psi. Now we don't know what the prior on psi is, but we don't need to. The point is that given any prior on psi, this evidence ratio, the thing on the bottom is just the expectation value of psi p to the psi minus 1. Okay? Expectation value over the prior, so given the prior distribution. As I say, we don't know what this is, but this expectation value on the bottom has to be at least, or no more than, the maximum of this function. So we have a function here with a certain probability distribution. Certainly the average value over psi is no greater than the maximum value. It's going to be less in general. So we have a limit for the term on the bottom, which tells us that the base factor has to be at least 1 over the maximum value of this function. So you can calculate that just using calculus, and that tells you that the base factor has to be at least minus EP times log p. This applies for p less than 1 over e, so quite an interesting calculation to do. It's slightly bizarre. So that's quite interesting. So we measure a value of p, and we can work out that the base factor has to be at least this quantity. You can also, in a frequentist way, say, let's express it in this base factor in a slightly different way, to say what is the probability of making a mistake by incorrectly rejecting the hypothesis. This is a type 1 error. So, and then that's given by this probability. So let's work out what you can work out what these error rates are, because you just basically work out this probability of a type 1 error as a function of p. It has to be at least this quantity. So if we take whatever value of p, we can work out this type 1 error. So 0.05, for example, gives you a type 1 error rate of 29%, at least. Right? So within this class of probabilities, if you do an experiment and you get a p-value of 0.05, you somehow maybe think, okay, the chances of the model being right are 5%, quite small. Absolutely wrong. They're at least 29%, and that's a minimum. Okay. So
let me ask one question. So if you think of the, standard back of the envelope, measuring with your hand kind of way, 0.05 is 95%, but 29% gives 1 sigma. So one is saying, I'm measuring 2 sigma, while in reality you're getting 1 sigma.
yeah. And actually, from what I've seen, I haven't looked at this extensively, but from what I've seen, if you do a mapping from one to the other, you basically lose one sigma. So if you get a 3 sigma result from P, then when you do these probabilities, it ends up being like 2 sigma. So subtract 1 as a rule of thumb.
That's why particle physics is 1.5 sigma and we are up in 3 sigma?
No, particle physics is a 1.5 sigma for some obscure reason that I don't understand. So this argument is based on assuming a family of reasonable alternatives to the hypothesis. The argument is a bit more general than that. The mathematics of this is just a little bit simpler. So it's not a completely general argument, because in general you would need to know really what the true probability distribution is, but it's a bit more general than this, but I think this is quite instructive. So what should you do as a Bayesian if you want to, you do your MCMC, you find your most likely parameters, how do you know whether it's a good fit or not? What should you do? Well, there isn't really a completely satisfactory answer to that, because there isn't really a way to do it, but there is something, you can get some way towards doing that by this argument, by using a thing called the posterior predictive p-values, PPP. Let me start out by looking at the prior distribution of the data. So, if you start with the prior distribution, then for parameters that are not fixed by the data, not fixed, rather, the sampling distribution is the probability of getting any data set. So if you marginalize over the unknown parameters, so let's say you have a model where you've collected some data in the context of a model with some parameters in it, then by marginalizing, then the probability of getting the data is the joint integral of the joint probability over theta. If you have some data, then the probability of getting a new data set, so let's say you collect some data, you do an MCMC, you get a posterior distribution for the parameters, then what you can do is to generate some artificial data and use that to inform you about whether the model seems good. So if the probability of generating a new data set, twiddles x, I'm sorry, I think in the first lecture I said twiddles means not, but here it just means some different data. So the probability of generating some new artificial data, given the data that you started with, is by marginalizing, it's the integral of the joint distribution of the new data and theta over theta, then you can use the rules of probability to write that as the probability of x tilde given theta and x times the probability of theta and x. This is what you've got from your first experiment, from your real data. You compute the posterior here, and this first term, the probability of getting x tilde given theta and x, well, this doesn't depend on x, this is just the probability of getting the new data given theta. So it's the sampling distribution for the model. So if we do an experiment, get the posterior, we can then generate some new data with a probability which is given by this. So here's the sampling distribution for the model. This is the posterior given your real data. So how can we use that? Well, what we can do is to define a test statistic, which might be chi-squared, it could be anything you like, and compute the probability, just a p-value, for the data drawn from the posterior, so-called posterior predictive distribution, the last thing. So you take some data, you calculate the test statistic for the real data that you've got, then do your parameter inference. Once you've got your parameter inference, then you generate new sets of data, taking into account, not taking just the best fitting parameters, but drawing the parameters from the posterior. So you have some random element to the parameters, generate some new data sets, and work out the probability of those new data sets, the probability of the test statistic. And the Bayesian posterior predictive p-value, PPP, is the probability that your simulated data sets have values which are more extreme than the data that you collected originally. So you can write that down as an integral. That's the integral of this probability distribution times, this is an indicator function which is 0 or 1, so it's 1 if the simulated data has a value which is more extreme than the data that you really collected. So this is better than the classical tests, because generally with the classical test, what you do is to take the best fit parameters and calculate chi-squared, or whatever the probability is, calculate chi-squared at the best fit point. But that doesn't recognize the fact that your best fit point is not necessarily the answer. There's an uncertainty of the parameters around that best fit point. So what this does is to include the uncertainty in the parameters that come out of your experiment. So it's better. It's not the full answer, but if you want to have a guide as to whether your model is really a good one or not, then this is probably the best that you can do. So it's not a formal answer to the question, is your model a good one? But as these probabilities are very low, then you might perhaps think, perhaps I need to consider a different model. Okay, I'm going to stop in a moment, but I just want to give you one extra slide which doesn't really fit in here, but just to tell you about it. This is just another extra thing that you need to consider. This is going back to doing parameter inference, just briefly. We've talked a lot about having Gaussian data and the Gaussian likelihood function, which is this thing here. Let's turn out the front, e to the minus chi-squared over 2. Just a word of warning that if you've got Gaussian data, then Gaussian distributed data, then the likelihood function is not necessarily Gaussian. That may seem strange, but very often the covariance matrix that we use for Gaussian distributions is not one that we can compute analytically. So it's very common to generate artificial data, simulated data, that are from an experiment which is similar to the real one. So generally, very often we don't know C, but we estimate it from a number of simulations. The more simulations you get, then the better result that you get. This can often be an expensive process if you're simulating, the Euclid BAO survey, for example. Then it takes a lot of time to generate mock catalogs and so on. So it might be expensive to do this, so the number that you can afford to do may be relatively small. If you do infinitely many, then you'll get a really good estimate of the covariance matrix. But if you're constrained by computer time, you may not. So, how do we treat this situation? Well, the first thing is to write down what is it that we actually want. Anybody think of an expression for the likelihood that we really want in this case? So it's not this thing at the top, P of x given mu and c. Because we don't know c. Anybody think? We don't know c, but what do we know? C hat. Right. So the quantity that we want is the probability of the data given the mean, which is a theoretical thing, and given C hat, also because it's relevant, the number of simulations that we used in order to get C hat. So that's the likelihood that we want, and that is not the same as the Gaussian one. So what you can do is to treat the C hat as a random variable. It's another random object. If you do some simulations, you get a different covariance matrix. So the Bayesian thing to do would be to marginalize over the true covariance matrix given your estimate of it. Okay, and that you can do. It turns out you can do it analytically. And it changes the Gaussian distribution into this thing here, which is a modification of the t distribution. So if you're ever using Gaussian data where the covariance matrix has been estimated from simulations, then make sure that your likelihood function is not the Gaussian likelihood function, but make sure it's this modified t distribution. It means changing one line of your code, so, and then you're properly marginalizing over the true covariance matrix and doing everything properly in a Bayesian way. Okay, I'm going to stop there, and I'm going to cover another topic in a minute. Are there any questions on any of that? Yeah. If your what is estimated?
What do you mean? It's also an estimation, not just a covariance matrix. That changes the like.
What is estimated?
Mean.
Okay. That's a good question. I don't know the answer to that. So normally the mean signal is. Yeah, that's a very good question actually. There's probably a paper there to work out what it is. Yeah, I don't know the answer to that. It'd be interesting to find out. So this properly marginalizes over the uncertainty in the covariance matrix. But you're right. If you get your mean by averaging a whole load of simulations, then there will be some uncertainty in the mean as well. So there will be an effect there too. Good point. I think the means the covariance matrices are quite difficult things to estimate. So I think probably you would be the uncertainty would probably be dominated by the uncertainty in the covariance matrix. But it's a very good point to make.
Nobody asked me to ask something. I think if you can characterize the error on the mean, you can propagate that into your covariance. And I think I've seen people trying to do that. But you need to know how to quantify the error on the mean.
Okay, so Bayesian exercise is to do this in a Bayesian way and see if you can, given a mu hat, say, you'll need to make some assumptions about the distribution of mu given mu hat. So if you assume, let's say, assume it's Gaussian, you've got enough. But, yeah, interesting problem. Yeah. Exercise for the afternoon.
You have to do it.
When you gave the example about the expansion, and you talked about you say that basically you can say your model is good or not according to the private. I understood that.
This one?
Yeah. According to the private. It's not something like misleading also. I mean, we're making kind of to say, to the private you choose, you can power your model or not.
Yeah. I don't think it's misleading. I think it's, with all of these Bayesian approaches, then your conclusions in principle do depend on what your prior knowledge was. So here, if you have essentially no prior knowledge, then you have to state what your assumptions are. So it is, I would say it's not misleading, it's just a genuine uncertainty, because here you really don't know what it is, so you make some assumption. But yeah, I share your nervousness, if you like. So generally, when I use these Bayesian evidence calculations, I would really only be certain that I would only trust the results if the Bayes factors were very large or very small. So anything that's near one, my prior uncertainty is important, then I wouldn't really want to make any strong statements. So I like it when the log of the Bayes factor is 40, then that's fine. I'm not worried about the prior there, because it might change it to e to the 39 rather than e to the 40. Okay, I'm going to change topic now. Do you want to have a short break before? Let's just take 5 minutes and then